Assalamu alaikum dear students, welcome to the lecture of the classical mechanics. In this lecture we will see the solution for the problem 7.31, which says a spherical pendulum consists of bob of mass m attached to a weightless extensionless rod of length L. The end of the rod opposite the bob pivot freely about some fixed point. Set up the Hamiltonian function in spherical coordinate. Okay, in this we have a spherical pendulum and we have to find the Hamiltonian function in spherical coordinate because it is spherical pendulum. So let's go to solutions. The very first thing that we will require, we can describe the spherical pendulum as a mass m moving in sphere with radius equal the length of a pendulum. The velocity vector in spherical coordinate can be written as, you know that velocity can be written as v is equal to r dot er plus r phi dot sine theta e theta plus r theta dot e theta. These are the velocity. These are the component of the velocity vectors in spherical polar coordinate. In our case, r is constant and its length of the pendulum, and it is the length of the pendulum L. The first term of the velocity vector vanished because r dot is radius is constant, so this will goes to 0, and the radius is equal to capital R, so it can be replaced by capital R phi dot sine theta e theta plus this whole term. Okay, so when we obtain, then the magnitude of the velocity will be equal to just r is equal to L, so L square phi dot square sine, because r radius is equal to length, so r will be replaced by length, and you know that the magnitude of the velocity will be component will be equal to v will be equal to one component square plus other component square and whole square root. So L square phi dot square sine square theta plus this whole square. This is the velocity, and then first we will find the Lagrangian, which is equal to T minus U. So kinetic energy is equal to 1 by 2 mv square and m over 2 and v square. We have already found the v. Just taking the square on the both sides, this will give v square, and plugging into this equations, this will give is equal to kinetic energy. Then potential energy, u will be equal to minus mgl cos of theta, because spherical pendulum like this will move in 3 dimensions, and this will be some angle theta, and similarly phi, and it will move in a circular in a spherical path. So and u will be equal to minus mgl cos of theta. Then for Lagrangian, which will be equal to L is equal to this is Lagrangian will be equal to T minus U. So we have kinetic energy, which is equal to this, and potential energy, which is equal to this. So just plugging these values in this expression, this will give Lagrangian is equal to this term. Okay, then the momentum, the conjugate momentum in theta and phi direction will be p theta is equal to partial L over partial theta dot, and p phi will be equal to partial L over partial phi dot. So just taking derivative of Lagrangian with respect to theta dot will give us p theta generalized coordinate, and similarly taking derivative of Lagrangian with respect to phi dot will give us p phi generalized momentum, and we can substitute from L to get this. Okay, then we can write the Hamiltonian. Hamiltonian can be written as, we know that Hamiltonian can be found by sum of p theta dot minus L. So because we have sum of p means the total number of the generalized coordinates, so p theta theta dot plus p phi and phi dot minus L. So we know that H is equal to p theta theta dot plus p phi dot and Lagrangian. We already found out the Lagrangian. We will plug the value of Lagrangian, and then we can put the value of theta dot and phi dot as we have found in the previous step, and plugging into this equation. So we know that p theta dot is equal to this and phi dot is equal to this, and using this theta dot and phi dot into this equation, this will give H is equal to p theta square over 2 ml square plus p phi square over this and this term. Okay, and it can be further simplified as this: p theta square over 2ml square, and this whole can be written as potential function or effective potential as given in the statement of the question, which will be equal to v of theta and p phi. So this is the Hamiltonian for the this dynamics, or this spherical pendulum, and these were the requirements of the question. So I will stop at this point and meet in the next lecture.